lecturer and peers. Today, our group addresses the foundational question driving modern chemical processing. Can this process be more sustainable? When evaluating Malaysia's industrial sector, the palm oil industry stands out as both an economic powerhouse and a massive environmental challenge. For this project, we have selected the palm oil industry waste management theme to critically analyze how traditional mining operations impact our ecosystem. More importantly, we are presenting a practical, closed-loop engineering improvement designed to drastically reduce emission and recover valuable secondary resources. Let's go live to our first analyze for a complete overview of the baseline industrial process.
To truly evaluate the sustainability of this industry, we must first examine how a standard palm oil mill operates. The primary objective of the mill is the extraction of crude palm oil or CPO from harvested fresh fruit punch. This is achieved throughout a sequence of intensive unit operation. First, the fruit bunch undergo steam sterilization to activate the hydrolytic enzyme and loose the fruits. Next, it will move to the stripping track where the fruits are separated from the empty bunches. The fruit are conditioned in a digester before it will mechanically screw press to extract the crude oil. Finally, the clarification steps will separate the oil from water and solid impurities. The economic importance of this process cannot be overstated. Malaysia is one of the world's leading producers of palm oil, turning this into the agriculture asset into a multi-billion-dollar export used globally in food, biofuels and oleochemicals. However, this massive output creates equally massive streams. Next, I will pass the floor to our environmental auditor to isolate the co-sustainability of the disease.
While the economic yields are high and the traditional waste management methods present a severe environmental challenge, our focus centers on two massive secondary streams, palm oil mill effluent foam, which is highly concentrated liquid waste, and empty fruit bunches EFB, the solid biomass residue left after stripping. For every single ton of crude palm oil produced, approximately 2.5 tons of foam is generated. Foam possesses an incredibly high biochemical oxygen demand (BOD) and chemical oxygen demand (COD). Historically, the industry treats this effluent with using vast networks of open anaerobic bonding lagoons. The primary sustainability crisis here is invisible atmospheric pollution. As anaerobic bacteria break down the organic compound in these open ponds, they release massive uncaptured volumes of methane directly into the atmosphere. Methane is a greenhouse gas with a global warming potential more than 25 times severe than the dramatically elevated of carbon footprint of the entire milling process. Additionally, millions of tons of solid EFB are either left to rot or open burn, causing localized land deterioration and severe air pollution.
To directly mitigate this climate and waste crisis, our group proposed a process intensification strategy, an integrated solid biogas capture and co-compositing system. We propose replacing or retrofitting the traditional open lagoon system with completely enclosed, high-rate anaerobic digester tank. By sealing this biochemical reaction environment, we successfully contain 100% of the generated methane gas, preventing it from escaping into the atmosphere. This captured biogas is continuously vacuumed, sent through a scrubbing unit to remove moisture and corrosive hydrogen sulfide, and route directly into a combined heat and power gas turbine. By burning the methane in the controlled engineering environment, we transfer severe environmental liability into a major utility asset. The turbine generates consistent renewable electricity that easily satisfies the mill's internal energy demand, with the excess green power capable of being exported directly to the local electricity grid. But to truly close the loop, we must also address the solid waste phase, which main college will explain.
Exactly. Our design achieves a true zero waste circular loop by combining the solid and liquid waste streams. The nutrition-rich liquid digest left at the bottom of our seal reactor is highly concentrated with nitrogen and phosphorus. We route this liquid to mix directly with the shredded empty fruit bunches that were previously discarded. This accelerated co-composting process yields a stable, high-grade organic biofertilizer. This fertilizer can be sent right back to the palm plantation, entirely replacing costly, carbon-intensive synthetic chemical fertilizer. We must, however, highlight the practical engineer challenges and limitation of this proposal. Implementing seal tank, digester and gas turbine demand a high initial capital expenditure. Furthermore, managing toxic gas impurities requires strict preventative maintenance protocols to avoid system corrosion. However, our feasibility and payback analysis prove that these investments are quickly offset by the continuous generation of free on-site electricity and the commercial value of the recovered biofertilizers. We must, however,
By engineering a transition away from open pond degradation and embracing integrated waste recovery, our proposed design proves that the palm oil milling sector can successfully achieve a self-sustaining circular economy framework.